Welcome, dear students. Now, today we are going to discuss about sequence of real numbers. Uh, Here you can see the slides. Okay, just let me start. First, we shall discuss about what is sequence actually. Before going to sequence, we want to discuss about function. What is function actually? What is function? Suppose you have two sets, A and B, A and B. Now, suppose this set is our A and this sets are our B. Here is some elements. This is non-empty. Here is some elements. If there is a rule which assigns every element, each element of of this set A to a unique element of this set B. This element, suppose this one small A1, A2, A3, and last one A4. If suppose A contains only 4 elements and B contains 4 or 5 or 6, maybe here 5 elements. Now, if there is a rule which assigns, suppose A be that rule, then F taking that A1 element to here some element B1, again A2 to some element B2, and so on. And if we see that every element or each element of the set A is connected with a unique element of B, then such a rule we call a mapping or a function. Now, if f be any function whose domain is the set of natural number and the codomain set is x, any function whose domain is set natural number, then that function we call a sequence. Now here, if that set x, capital X, if this x be set of real number, then the sequence we say this is a real sequence. And if this be our, suppose this be C, set of complex number, then we say this function is a complex sequence. Now, we can give examples of functions whose domain is set of natural number. Suppose f such that n to r and fn is equal to n. Fn is equal to n means 1 is going to 1, 2 is going to 2, 3 is going to 3. That means x is going to x actually. Then this is a function, clearly every element of the domain set, that means natural number, has images in codomain set, that means in real number. So here we can say this is a function, and this function with domain natural number. So this is a sequence, and since codomain set is real number, so this is a real sequence. Now we denote this sequence by this notation, only by fn or by the values of fn. So this n is a sequence. And similarly, we can denote fn equal to n square. So we can get so many sequences. N square, 1 by n, 2n plus 3. So many sequences we can give for it. We can get. Now, if we discuss about this one, n, then we can express the element of this sequence as 1, 2, that means 1 goes to 1, first term, this 2, then 3, this third term, 4, and so on. Now, for this one, you can say this is nothing but our first term. We can say this is our x1, and this is our x2, this is our x3, and this is our x4, and so on. Now, for this one, for this sequence, we also denote this sequence by xn. where xn is equal to n, the nth term of the sequence, this xn is n. Now for this one, if we say that the every term here, the second term, first term, here you can say 1 less than 2 less than 3 less than 4 less than dot dot dot, and then this is our actually first term x1 for this particular sequence. This is second term, this is third term, and so on. Now in general case, or generally we can say xn plus 1 for this particular sequence greater than xn. So if this happens for all n, then we say the sequence is monotonically increasing. So a sequence xn is said to be monotonically or monotonic increasing. Monotonic increasing if xn plus 1, that is the latter term, is bigger than the previous one for all. Yeah. And equal to may occur if strict inequality occur, then strictly monotonic increasing, otherwise just simply monotonic increasing. Now here you can see for this sequence 1 by n, for this one, this sequence actually, if we write all the elements of the sequence, then this is nothing but our xn is here. Xn is the sequence, and nth term is denoted by xn is equal to 1 by n. What is the first term? Any sequence xn, we denote this one by x1, then x2, then third term x3, x4, x5, and so on. Now for this one, xn equal to 1 by n, first term is 1, second term is half, 1 by 2, this one 1 by 3, this one 1 by 4. Now for this one, you can see the first term is this one, 1. Second term is less than the first one. Third term is again less than the second one. So here xn plus 1 actually less than xn for all n. For this kind of sequence, we say this is monotonic decreasing. If for a sequence, if for a sequence xn, if for a sequence xn, this holds xn plus 1, the next term is less than the previous one for all n or equal to may occur, then we say then xn is called a monotonic decreasing sequence. A monotonic decreasing sequence. Now there is a simple question. Can a sequence at the same time be monotonic increasing and monotonic decreasing? Just think about it. Can a sequence xn be mi monotonic increasing and monotonic decreasing at the same time? Just think about it. Now we are coming to our next question. What's the limit, or what is the convergence of sequence? What do we mean by convergence? What do we mean by convergence sequence, or what is convergence sequence? Okay, just first draw the picture of this one. Xn equal to 1 by n for this one. for this sequence xn, where xn is equal to 1 by n. For this one, suppose this point be 0. Here be x1, 0, 1. Then obviously here is this point is our half. This point is half. This point is 1/3. This point is 1 by 4. Suppose this one be 1 by 5th, 1 by 6, 1 by 7, dot, and so on. Now, for this one, now I am just changing the color of this one. Suppose this one our x1, first term. Not suppose. This one actually our first term. X1 is 1. And then this one x2, our second term. X3, this third term, this is x4. Now you can see after some particular time, you can see we will get, if you take a small neighborhood of 0, then you can say after some particular term, every term, all the terms of the sequence will lie inside that neighbor. So if it happens that after some finite number of terms, all other remaining terms belongs to a particular neighborhood, inside a particular neighborhood, and if that happened in every case, then we say that sequence converges to that particular number. Or clearly you can see here. Okay, first I want to give you the formal definition, then we are coming to the explanation. What is the definition of convergence of a sequence? Let xn be a sequence. Let xn be a sequence, and L belongs to real number, be any real number, and L belongs to real number or be any number. Be any number. Now xn is said to converge to L if for every given epsilon greater than 0, every given epsilon greater than 0, there exists a natural number. M belongs to set of natural number such that this condition hold. Modulus value of xn minus L less than epsilon for all n greater or equal m. This happen. Now, what does it mean? Xn modulus value of xn minus L. Now, xn is also a real number and L is also a real number. Modulus value means the distance between that two number. Now, this actually indicates that if L be any real number and xn be a sequence, if after that term, actually if we express this one, mod of xn minus L less than epsilon, now this one, what does it mean actually? Mod of xn minus L less than epsilon. This actually implies L minus epsilon less than xn less than L plus epsilon for all n greater or equal m. Suppose this be our L. We can change the color of this one. L, this is our L. Now, this is our epsilon b. We are taking epsilon this distance, epsilon. This is our L minus epsilon. And then this one our L plus epsilon. Now, here you can see that the sequence has so many terms. The sequence has so many terms, x1, x2, x3, dot up to xm minus 1, then xm, then xm plus 1, after that xm plus 2, and so on. Now, this is our xn sequence. Now, this definition basically tells us that that all the terms, including mth term, and then after the mth term, m plus 1 term, m plus 2, m plus 3, m plus 4, all other terms will belong to that interval, L minus epsilon to L plus epsilon. That means here, this x1, this x1 may belong to either uh, outside or may inside. May outside, this may belong up to x n m minus 1. All this m minus 1 number of term, that may this all this term up to this term, this may belong outside L minus, outside this interval. Maybe left side of L minus epsilon, or maybe right side of L plus epsilon. But after that m minus 1 term, that xm starting from xm to all other remaining term, this all term must belongs to here only L minus epsilon to L plus epsilon. Okay, let us take an example for this one to clearly understand this one. This definition, actually, definition of convergence of sequence. Now, for example, we are taking the sequence 1 by n. 1 by, this is nothing but this sequence over 1 half, 1/3, 1 by 4, 1 by 5, and so on. Now, okay, can you give me an example? Can you give me a value of epsilon? Just think, all of you just think about the value of epsilon. Okay, suppose I am taking the value of epsilon as 1 by 10. Then here you can see all the numbers are going towards 0. So by a simple assumption, we can say that after some terms, all terms are going towards 0. Going towards 0. That going very close and close to 0. Now, if limit exists, then we can assume that that limit will definitely be 0. Okay, 0 is our L here in that case. 0. Now, what is our 0 plus epsilon, 0 minus epsilon? That is minus 1 by 10, 0 minus 1 by 10, and this side 0 plus 1 by 10. Now, what is the value of x1? The value of x1 is 1. As you can see there, x2 is half. Okay, up to this one, x9, you will get 1 by 9. And then x10 is 1 by 10. x11 is 1 by 11, and so on. Now, here you can see that x1 is 1 for this one. x1 is 1. Okay, we are changing the color, this one, 1. Now, this is our 1 by 10. If 1 by 10 be here, then 1 suppose here, 1. You can see clearly 1 is outside that region. Now, 2, half. Half definitely will be here. Maybe here, half. Half is also outside. Okay, then 1 by 3. 1 by 3 is also outside. 1 by 4 is also outside. Then up to this one, we can conclude that if suppose 1 by 9 is here, this one as our 1 by 9, then 1 by 9 also belongs to outside of this 0 minus epsilon and 0 plus epsilon interval. But 1 by 10, just on the boundary. So we cannot take this one inside. This is on the boundary. Boundary means, and since we are taking this one as an open interval, so we cannot say 1 by 10 belongs to that interval 0 minus epsilon, comma 0 plus epsilon. No, that is outside point. Now, if we think about 1 by 11, then definitely 1 by 11 belongs to inside that interval. Then 1 by 12 also belongs to that interval. 1 by 13, 1 by 15. That means our x11 belongs to here. Also x12. x12 also belongs to here. Now you can think about x10 million term. Then x 1000, x 100, x 1000 term, x million that also belongs to here only, slightly right side of 0. So we can say that in that case, we can say that all the terms after 10 number of terms, after x10, all the terms belongs to that interval 0 minus epsilon, 0 plus epsilon. So here we can say for epsilon, if you give me epsilon 1 by 10, then we can say all the terms here xn belongs to 0 minus epsilon, 0 plus epsilon for all n greater equal 11. So this 11 is nothing but this 11 is our m, the value of natural. Now if you give me the value of epsilon 1 by 11, then our m will be 12. If you can give this one 12, then our m will be 13. And so if you give me any epsilon, whatever the value of epsilon, that may not be in this term p by q type or 1 by something. You may give me root 2, 1 by root 2, any value, any real number. If you give so small value, maybe bigger value also you can give, then automatically that will be inside that one. That is very easy, easy case. Now, whatever the value of epsilon, suppose you are giving me the value of 1 by 100, then definitely our aim will be our 101. In that case, so we can say for all epsilon greater than 0, we can say mod of xn minus 0 less than epsilon for all n greater equal m. That means for every time, whatever epsilon you will give me, I can give you an m. I can give you an m natural number. So this hold every time here. So this basically satisfies the definition of convergence. So from here we can say this our sequence xn converges to the real number 0. And also we write this one as xn tends to 0. That means xn converges to 0. Also in limiting form, we say limit n tends to infinity, xn is equal to 0. Here, this definition also we can say in another way that a real number L. Also, we can say a real number. Hope you understand the definition of the convergence. What do we mean by convergence? The same definition here in this definition. Also, we can say this L as the limit of the sequence. Or this definition, the limit of a sequence, we can give the definition as this way: a real number L is said to be the limit of a sequence xn if for all epsilon greater than 0 there exists natural number m such that mod of xn minus L less than epsilon for all n greater equal. That is the definition of convergence of a sequence and limit of a sequence. Just depend on the terms. Both are the same. When we say a sequence converges, then it converges to a real number. That real number is called limit. And if a sequence does have limit L, then we say the sequence converges to that limit. Also, here is one important result. If limit of a sequence exists, then it is always unique. If limit of a sequence exists, then it is unique. then it is unique. Okay, here you can see the proof. This is a theorem. This is theorem. Here is the proof. Okay, suppose we are assuming that there are X and B sequence and it has two limits, L and L prime. And then we can show that if the limit exists, then L and L prime will be equal. Okay, let X and B sequence, X and B sequence, and suppose it has two limits. It has two limits, L and L prime. Then for epsilon greater than 0, what we can say? Mod of xn minus L less than epsilon for all n greater equal. For this epsilon greater than 0, we will get a number, natural number. There exists m1 belongs to natural number such that this will hold. Mod of xn minus L will be less than epsilon for all n greater equal this m1. Now, whenever xn minus L less than epsilon hold, so epsilon is an arbitrary number. Now epsilon by 2 is also an arbitrary number. So instead of writing epsilon, we can put here epsilon by 2. Also, if we don't put epsilon by 2, then also we can prove. No problem. Now also, xn minus L prime, this will also be less than epsilon by 2. Now also L prime. Okay, just 1 second. We have to write one more lines. Also L prime is a limit of xn. So for epsilon greater than 0, there exists m2 also. We shall get another natural number m2 such that our mod of xn minus L prime will be less than epsilon by 2 for all n greater equal that m2. Now, if we take the maximum of this m1 and m2, now we choose m as maximum of m1 comma m2, then we can say that both the conditions, then our for all n greater equal m, we can say mod of xn minus L less than epsilon by 2, mod of xn minus L prime less than epsilon by 2. This both holds. This both hold. Okay, for this one, you can say, suppose I am giving an example that suppose the boys whose age are bigger than 10 can play football, and the boys whose age bigger than 20 can play cricket. Now, if I want the age group who will play both cricket and football, then I have to take the maximum of bigger than 10 and bigger than 20. That means if I choose bigger than 20, then that will play both football and cricket. That is why here also we can choose m maximum of m1 and m2. Then this can hold. Okay. So now L minus L prime, if we calculate this one, we can write L minus epsilon by 2 plus epsilon by 2 minus L prime. Now this one we can write uh, here, sorry, just not epsilon by 2 or this one. We can add and subtract here xn or this one, but this will not work. If we write epsilon minus 2 or epsilon plus 2, this will not work. Now we have to take xn plus xn. Now here you can say we can write this one as this one and this one. Then this one is also our less than epsilon by 2. This one also less than epsilon by 2. So we can say mod L minus L prime less than epsilon. So this for if this happens for every epsilon greater than 0, any arbitrary chosen number epsilon, you will get always less than this one. So it basically implies our mod of L minus L prime, obviously this should be 0. This implies for arbitrary epsilon, for arbitrary value of epsilon greater than 0. So here we can say both are same. Hence, limit if it exists, hence limit of a sequence is unique. Limit of a sequence is unique when if it exists. If it exists. Okay, thank you. Today we stop here. Maybe in the next class we'll discuss some more important results and theorems and some interesting problems. Okay, thank you.